All right. Hey everyone, it's Matt. In class we were talking a lot about counting. Now we will get some probability rules. These will help us to combine different things, to combine the probabilities of different events that we may know. Let's start just with a couple of axioms here, some probability rules. These should be mostly intuitive. Let's go through them. So if an event is impossible, we'll say it has probability 0, or maybe 0%. Something's not going to happen, 0%. Something that's certain to happen, something that will for sure happen, is 100% likely, or probability of 1. For the rest, that leaves us that the probability of any event A that we're interested in will have a probability between 0 and 1 inclusive. So these are axioms. These are things that we decide or define right on the top, and we'll use them in what follows. Let's go through and define a couple of things. So let's think about complementary events. We may have sort of the complement of event A that's denoted A bar, like this. This is basically saying not A. So this is the outcome in which our event A does not happen. Based on kind of more or less logic, we can think that we have this formula here, where the probability of A happening and the probability of not A happening is 1. So either A is going to happen or A is not going to happen. This is the space. These are the only possible options. One can kind of illustrate this with a Venn diagram. We'll see more Venn diagrams later. This one is fairly simple. We have sort of A happening here, and not A is outside. This whole box here is our universe, all of the possibilities in our sample space. So for example, if we were thinking about the experiment, let's roll a die. If it's even, we win, that's A. If it's odd, that would be in the A complement. So inside of A, we can have different options, like the possibility of rolling 2, 4, and 6, whereas in the complement, we have all the other ones, 1, 3, and 5. Why do we go through this? Well, in addition to being true, it also sometimes is convenient for us. It may happen that it's easier to calculate the complement of something and then just flip it on its head. So we can use this a little bit later in class in the birthday problem, sometimes called birthday paradox. It's an enjoyable and counterintuitive problem that we'll go through a little bit later. Now, to ramp up the complexity here, we can think a little bit about compound events. So we can take 2 or more simple events and imagine combining them. We can use the following notation here. So we use the cup notation here to specify or, and we'll use the cap sort of symbol here to represent and. So for example, if we're thinking about the probability of A or B happening, that will be the probability of A plus the probability of B. And then we'll have to subtract out the probability of them both happening to avoid some double counting. We can go through and explain this maybe in a Venn diagram to see some example. So let's come down here for graphical explanation of this addition rule. Addition rule. So let's consider the following sample space. Let's have a bit for A, and let's have a bit for B, where the 2 of them may overlap. So there's A and there's B. If we were to think about all of the possibilities for A, that would be all of this. So the probability of A is all the stuff inside A. The probability for B is all the stuff inside B. Now, if we were to take all the stuff inside A and add to it all the stuff inside B, we're kind of doing a double counting. So this shaded area here is getting counted twice. So when we were shading, we filled this in twice. It was shaded twice. Once red, once blue. And so we'll need to subtract off one of the shadings because it was double counted. This is the reason for our rule. So we have probability of A plus the probability of B less the probability of both. This whole box here, of course, is our sample space. Intuitively, you can think of perhaps drawing from a deck, and you want to know if you can draw perhaps a red card or a king. There are some red kings that if you think about drawing all the red cards and think about drawing all the kings, you will double count drawing the red kings. We'll see example like this again as we go through, but let's start out with some, let's go through a few examples. We'll start small and we'll keep building up. So let's start here. Typical multiple choice test question. You've got about 5 possible answers, and maybe you don't know what's going on. You can make some random guess. What's the probability that your response is wrong? Well, it's pretty easy here to think about the probability of getting the correct answer. So that's the number of correct responses over the total number of answers. There is only one right answer in this particular test question. There's 5 questions in total, so we're looking at about 20%. We could compute the probability of getting it wrong using the complement rule, so we could just take 1 minus p of the correct. So 1 minus a fifth, or 4/5. Now this example is a little bit simple. I'm sure you could have said, oh, well, there's 4 wrong answers and there's 5 total, and do this without using the complementary rule. That would be perfectly satisfactory, but we will use this rule of complement several times throughout the course. So right here, what's happening is we're getting our rule of complements. Okay, so let's move on to another example here. We can imagine thinking about having 3 kids in total, and perhaps we will be particularly interested in the possibility of having exactly 2 boys. For this problem, let's assume that boys and girls are equally likely and that we get each both with 50%. It's not quite right, but let's simplify things in this way. So let's denote B for boy, G for girl. Now, what we're going to do here is outline a tree diagram for the sample space. So this is a process you can go through to visualize all the possible different outcomes that could happen, and they can be used in calculating different probabilities. So you can imagine here, starting off, you have 1 child. You get boy with 0.5% or girl with 0.5%. That's sort of your first move, so to speak. And then we can continue. Once you've had either a boy or a girl, you can imagine having another child, of which there are again 2 options. So boy with 1/2 probability, girl with 1/2 probability, boy with 1/2 probability, girl with 1/2 probability. So that's 2. We can do this one more time. Each particular option that we've had so far can again be split into boy or girl with 1/2 probability each. Like so. And since all outcomes are equally likely, we can imagine investigating each of these for our desired outcome. And then comparing that to the total. So just to make things easier, let's denote the first one boy, 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 followed by boy, boy, girl, boy, girl, boy, and boy, girl, girl, and so on. Down the line here. Now we start girl, girl, boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. Okay, so all the outcomes here, based on what we've said so far, are equally likely, but there's a few that we are interested in. So the 2 boys are coming here, here, and here are the 3 possible outcomes involving 3 boys total, and so we can compute this by taking the ratio. All outcomes are equally likely, as we say they are simple events. And the probability we're interested in, exactly 2 boys, is going to look like the total number of outcomes with 2 over just the total in general. There's 2, 4, 6, 8 in total. So we get 3 on 8, or about 37.5%. Okay. Let's press on here. Let's do this next example, this dice game. We're going to roll a pair of dice, and we will list the possible outcomes and then find the probability of rolling a 7 or an 11. So we have seen this sample space before. You can imagine rolling a 1 and a 1, a 1 and a 2, a 1 and a 3, all the way up to 1 and 6, or a 1 and a 2, 2 and a 2, etc., all the way down to 6 and a 1, and 6 and a 6. So this is our sample space here. Previously, we've said there are 36 outcomes. And these are all simple events. Now, the probability of rolling a 7. How many total outcomes have a 7? Outcomes with total of 7. 1 and 6 make 7, and we subtract 1 and add 1 to each. 2 and 5, 3 and 4, and then the flips on the way back. 6 and 1. There's 1, 2, 3, 4, 5, 6 possible ways here. So 6 on 36 ways to make a 7. probability of 11 here. Let's consider the outcomes with 11. Uh, 11 we can only make with 5 and 6 or with 6 and 5. So there's just 2 on 36 here. So if we wanted to think about combining those, we could imagine thinking about the probability of 7 or 11 happening. Using our addition rule, that would be the probability of 7 plus the probability of 11 minus the probability of them both happening. Interesting thing to note here is that when you roll the when you roll your pair of dice here, it's not possible for you to get both a 7 and an 11. The total is either 7 or 11. So this particular one here is impossible. You can't roll a 7 and an 11 at the same time. And so its probability is simply 0. So when we crunch this out here, we'll throw in our 6 over 36 and our 2 over 36 and just have 0, just subtract 0, which is the same as adding 0, for the and here. So that gives us about 8 over 36, which we could simplify or write in decimal, about 22%. Now, so these two events that we were thinking about, their and was 0. They cannot occur simultaneously. We have a name for this sort of thing. We'll use the phrase mutually exclusive events. So events that have this property where the probability of A and B is 0, we will refer to as mutually exclusive. In the Venn diagram here, that would look something like this. A is over here and B is chilling over here. The two of them have nothing to do with each other. They are independent. They are mutually exclusive. They cannot occur simultaneously. So as we just saw in the past example, the addition rule simplifies a little bit. If the probability of A and B is 0, we can neglect this last term and simply do the intuitive probability of A or B is probability of A plus probability of B. Okay, let's think about drawing the top card from a deck of cards, maybe after some shuffling, and think about the probability of selecting a red card or an ace. This particular example you would say is not mutually exclusive. It is possible to draw both a red and an ace. That would be, of course, a red ace. So let's write this out. We can have R, B for red, and A, B for ace. We can consider the probability of red and ace to look like the probability of red plus the probability of ace. Now we must subtract off the probability of having both. This is again to avoid the double counting. So in total here, the red cards, half of the cards are red, so that's 26 over 52. These are all of the red cards. 26 total red cards. There are a total 4 aces in the deck, 4 on 52. Here are our aces. Now, if we stopped our equation here, we've added up all of the red cards, we've added up all of the aces, but the red aces fall into both of these camps. 2 of the 26 here and 2 of the 4 here are the 2 red aces, and so they've been double counted, so we must subtract them off once. Let's subtract off the probability of getting a red ace, of which in the decks there happen to be 2 hearts and diamonds. So here we're subtracting out because of the double counting. The double counted red aces. So in the end of the day, we're getting about 28 over 52, or about 54% here. So this is an example where the events are not mutually exclusive. We will also throw around these words independent and dependent. Two events A and B are independent if the occurrence of one does not affect the occurrence of the other. If they are not independent, well, then we say they're dependent. It's one or the other. We have a little bit of notation for this. So this bar here, probability of B bar A, that will tell us, or that will represent for us, the probability of event B occurring, assuming that A has already occurred. So you might say in words, probability of B given A. Okay, we can have a multiplication rule. So we had an addition rule for OR. There's a multiplication rule for AND. So if we're thinking about finding the probability of A and B, if they happen to be independent, we've talked a little bit about things like this before. You can just take the product. If they are dependent, then you'll have to use this slightly more different product, coming using the probability of B given A. So let's turn to see this happening by means of two examples, one for each formula. So let's consider the probability of getting two heads with two flips of a fair coin. We can flip this toonie over here. Let's let maybe HI mean heads. On flip I. Flip I. I here is either 1 or 2. We're going to have two flips, flip 1, flip 2. So let's consider the probability of getting head on the first and on the second. These two events, the flipping of the second coin cares not what the flip on the first coin got. These two are independent, so we can use the independence product rule here, thinking that the coin flip on the second flip is impacted by the first is the gambler's paradox, so don't gamble. We can use this since coin flips are independent. Just because it came up 100 times heads doesn't mean the next one is any more likely to be heads. Probability for each is a half, and so in total we get a quarter. We've seen things like this before. Now let's do a different one. Let's think about drawing two cards at random from the deck, and think about the probability of getting a pair of aces. Two aces, very desirable hand. Let's do same. Let's have AI mean an ace on draw I. I here being either 1 or 2 for the two different draws. Now there's two different ways we can play this game. We can imagine replacing the first card before the second is drawn and shuffle up the deck, draw a new card. Or we could not replace. This is sort of without replacement. So we draw from the deck once, and then we continue using the same deck. We draw another card from the deck without putting back our first card because we'd like to have two. This gives for us here some dependence. Whereas with replacement, we would say these two are independent. They care not for each other. They don't have anything to do with each other. Independent. All right, let's solve each of these two in order. So let's consider A. So we can, again, think about the probability of getting A and A1 and A2, aces on both. Since we are replacing and shuffling up again, the case here is independent. There are total 4 aces in the deck, 4 on 52, times another 4 on 52, which gives us this small percentage here. Not super likely, it's a pretty good hand. Now, if instead we wanted to turn our attention to B, we will consider these two to be dependent. It matters what happens on the first, since we are not going to replace the first card that we draw. So in the dependent case, if you draw an ace on the first draw, this will impact your chances of drawing an ace on the second draw. So if you happen to get lucky and select an ace on the first draw, now there are only 3 left in the deck. So your chance of an ace on draw 2 is going to look like 3 over 51. There's 3 aces left in the deck, and there's only 51 cards left in the deck because you've selected one of the aces. However, if you don't draw an ace on the first draw, on draw 1, lots of other things could happen. This will impact the probability as well. There are no aces yet have been drawn. There's still 4 in the deck, but there are 51 cards left remaining themselves. So this top number here is how many aces are left, and the 51s are just the number of cards left. Okay. Let us use these here to solve our problem. So we're interested in the probability of getting 2 aces, a pair of aces. We will use the multiplication rule for dependent events, as shown here. So we'll find the probability of selecting an ace on the first draw, which is 4 over 52. But now we have to multiply by the probability of getting an ace on the second, assuming or under the condition that we got an ace on the first one. That we have done over here. That was this first case here, assuming we got an ace here. Then we will pull in this 3 over 51, the chance of us getting that second ace. This gives us a slightly smaller probability, since one of the aces is already gone, and there's lots of cards in the deck. It's harder to get the second ace than it was just to get 2 aces together. So you can notice that these numbers, let's do green. Oh yeah. You can notice that these 2 numbers are slightly different. It may seem like a slight thing, but when you play games lots and lots of times, as people in a casino might, eventually these small numbers will make some difference, and that's how the house will always win. Okay, we'll pick up here next time in class, thinking about some more different probability games and combining them together.